Hi, my name is Lucas Sanchez, and today we're discussing flow systems and the energy of the system. So, as we know, the energy of a system can be expressed as the um, internal energy plus the kinetic energy plus the potential energy per unit mass of the system. But we want to focus on changes in a flow system. So we're going to take the differential of the energy per unit mass in the system. And we know that in a flow system, it can be brought about by adding a flow rate in. And the flow rate in can have an internal energy, can have a kinetic energy, it can have potential energy per unit mass in to the system. And then obviously we have a flow rate coming out of the system as well. So we can have all those same things: internal energy, kinetic energy, potential energy per unit mass flowing out of the system. We can also work on a system by adding heat to the system or adding work. But work can be two types of work here. It could be non-flow work, or it could be flow injection work. And flow injection work is equal to the pressure times the differential amount of volume that flows in. That's what flow work is equal to. We'll say flow work is equal to that. But since we have differential mass here and here, we want to somehow express this as the mass, differential mass that flows in. So we could use the relationship between density, between mass and volume. As we know, that's what density is, the relationship between those two, to kind of simplify this in terms of the differential amount of mass coming in the system. So pressure over density times dmn will give us this expression, because it'll be pressure times times volume over mass times dmn. These will cancel out and we're left with pressure and volume still. So we can go ahead and rewrite flow work as this expression here. So let's change our equation a little bit. Non-flow work plus P1, we'll say P1 is the pressure of the flow rate in minus P2 over the density of dm out. Now, to simplify this expression even further, we can go ahead and use the relationship between enthalpy, pressure, and internal energy. Because we know enthalpy is equal to U plus PV. And since this has dmn attached to it, we can go ahead and throw it in here, and since this is dm out, we can throw it in there. And we'd have U plus P over density times dmn, or slash out. And like I showed before, pressure, or density and mass will cancel each other out, and we'll be left with U plus PV again. So we can change this expression out one more time. Instead of U plus P1, or pressure over density, we can label this enthalpy. So let's write that as such. So we're going to be left with this will stay constant, but it's going to be equal to now, like I said, H plus 1/2 V squared plus GZ times the differential amount of mass going out of the system minus H plus 1/2 V squared plus GC times differential mass out of the system plus heat plus non-flow work. And this is expression for the energy of a system and the differential of changes of energy in the system. And then we can use this expression to derive a very useful equation known as Bernoulli's equation, which allows us to solve some pretty practical examples of flow rates in and out of systems. So let's go ahead and derive Bernoulli's equation. So let's say we have a steady state, and that means this term here becomes 0 because there's not going to be any changes in energy in the system. It can be left as 0. So 0 is equal to this whole expression here. And for our sake, we're going to go ahead and kick h back. H is going to become, again, H is becoming P1 over density plus U. And this is, this is P2 here. So will now become P2 over density plus U. So what we're going to do is we're going to group these terms, both these terms, as just dm, and then simplify this expression so it's a little bit cleaner for us to use. So we'll say, I'm going to say u1 minus u2 plus v2 squared minus v1 squared over 2 plus g times z2 minus z1 plus p2 minus p1 over density. And that's all times differential of mass. And this is all equal to 0. 0 is equal to, and this still has heat and non-flow work here. And what we're going to do is we're going to group some of the terms here and switch them on to the other side. So let's move all of these terms here on the other side of the expression. So we're left with v1 squared minus v2 squared over 2 plus g times z1 minus z2 plus P1 minus P2 over density is equal to U2 minus U1 plus dQ over the differential amount of mass plus dWnf. So this becomes Bernoulli's equation here, and we can use this expression to solve different flow systems and different properties of these systems. So let's go ahead and take a look at an example for one of these problems. All right, so let's say for this expression, or for this example here, we're using Bernoulli's equation, we have a horizontal pipe. And on this side of the pipe, we have water flowing in at a pressure of, let's say, 10 to the 6 pascals, and it has a temperature of 298 kelvins. So that's the flow rate in. Flow rate out here will have a pressure of 10 to the 5th pascals. And we don't know the final temperature, so T2 is unknown. But how are we going to solve for that? We're going to use this expression here that we just derived. We're going to assume we're going to make some assumptions so it makes simplifying this expression a little bit easier. We're going to assume that the speed of the velocity of the water is flowing in at the same rate that it's flowing out. So we can cancel out this term here. As you can see, it's a horizontal pipe, so there's no change in potential energy here. Pressure obviously is changing, so we're going to keep this term around here. We're not adding extra heat to the system, so that's out. And we're not doing any more work on the system, so that's out. So we're left with here is P1 over P2. So the change in pressure over density will be equal to U2 minus U1. And as we know, internal energy in the system is just a proxy for temperature. So that's going to be the key to solving this problem. We're going to express U2 and U1 as CV, the heat capacity of water, times temperature 2 minus temperature 1 will be equal to the change in pressure over the density of water. And now we have all the unknowns that we need to solve for this expression, except for T2. And we can solve for T2 because we know everything else in the expression. So P1 minus P2 is going to give us a value of 900,000 over density. Density is going to be 1 kilogram per cubic liter. Or per, no, sorry, it should be, yeah, no. It's going to be 1,000 kilograms per liter. What am I doing? Yeah. Pascals, kilograms per liter is equal to CV. The capacity of water is, I think, 4,184 kilograms per Kelvin. No, so there's another. Oh, per kilogram. No, it's joule per kilogram Kelvin. Joules per kilogram times Kelvin. And then that's going to be equal to T2, which we don't know, T2 minus T1, which is 298. So we go ahead and simplify this. This becomes 900, and then divide it by 4,184 equals T2 minus 298. So T2 is equal to 298 plus this number, which I believe is around 0.215. 215, we'll say. So T2 is equal to 298.0 or 0.215 Kelvin. So that means the change in temperature here is around 0.125 kelvins as water flows in and out of the system. But there's still one more example we want to take a look at before we conclude the video. So stay tuned. All right, let's take a look at another example here. Let's say we have a tank of air. So let's say the tank of air here. And we have a pressure of 10 to the 4th pascals here. Oh my God, that's horrible. 10 to the 4th pascals inside of the container. And we want to figure out the velocity of which the air flows out of the system. And we can do that, again, using Bernoulli's equation that we just derived. So it's a steady state. So none of this stuff on this side is going to be changing since we're at steady state. So we're going to say V1 squared minus V2 squared over 2. And then again, we're going to neglect this change in height here. Just cancel this term out to make it easier for ourselves. Plus P1 minus P2 over density equals 0. So we have everything we need. We assume that there's no flow rate in, so this is just 0 here. So we have V2 squared over 2 equals P1 minus P2 over density. But we don't know the density of the air, so we have to somehow calculate that. We know density is equal to mass over volume. And we're talking about gases, mass is usually equal to the number of moles times molar mass over V. PV equals RT. So what is N over V equal to? N over V is equal to P over RT. So we have PM over RT. The only problem is we don't have the mass of the air. So density of air is equal to. But we can solve this by using a simple calculation. So it's going to be the number of moles. We know air is composed about 79% of nitrogen and 21% of oxygen. So it's going to be 0.79 N, number of moles of it, times, what's the molar mass? It's 28 grams for nitrogen plus 0.21 times moles over 32 grams for oxygen over the number of moles. This will cancel, this will cancel, this will cancel. And we're left with mass of air being about way off the screen. Sorry. The mass of air is going to be about 1.2 grams here. So density, we can solve for here, is about, this is not 1.2. This is about 28 grams here, 28 grams here. But we plug in everything we know for the air. The pressure is about 101,325 pascals times the massive calculator for it, times 10 to the negative third, over the gas constant, times temperature, which we assume 298. We get density to be around 1.2 grams here. So we can then solve for differential here. So now we have it all, and then we can solve for V2. So V2 will be equal to square root of 2 times P1 minus P2 over that. I think okay, so P1 is 10 to the 4th minus P2 is 0 over 1.2, 2 times that, so what we get number, let's see what we get. 10 divided by 1.2, square root of that, 91 meters per second that's going to flow out. So that'll be the velocity of the air exiting the system. I made a mistake on the calculation in the last part of the video. This is inside the parentheses here. So that changed our number to about 129 meters per second for the velocity of air exiting the container. Sorry about that.